So here's a small update about the constant jerk planner I'm working on for Marlin. And I made myself a small simulator that still runs C code. This is a web page, but it is running C code compiled to WebAssembly, so I can play with it and see how it behaves. Like just using test cases was really not working for me. So I set this up so that we can see the classical trapezoidal acceleration profile, the kind of trajectory that Marlin currently uses. And we see here we need to travel 35 millimeters with some maximum acceleration, having and the defined entry and exit speed. And what the trajectory of this looks like is there is an acceleration phase, a cruise phase, and a deceleration phase. And this is not super hard to calculate the shape of these phases. The issue this has is that acceleration is a discontinuous function. So you can see it here, this the staircase. And this causes two issues, this discontinuous acceleration curve. One is resonances. This tends to excite resonances in the 3D printer. And the other one is linear advanced. Because the formula of linear advance has a term which is the derivative of extrusion times a constant times k. And so when you calculate the rate of extrusion, you have what you plan to extrude plus a discontinuous function times a constant, and that makes the whole result in a discontinuous extrusion rate. And the universe really does not like discontinuous velocity, so it does not like things changing speed instantly. And that's why the original linear advanced implementation used to limit acceleration, so that this discontinuity was bound. It was small enough that the extruder would cope anyways. And that's why me and others put so much effort into smooth linear advanced and then axis smoothing for FT motion, so that even though extrusion is discontinuous, the extruder can cope with that because we make it artificially smooth. Well, the extruder won't skip, but we're still introducing errors or we're not doing exactly the planned extrusion, so there's still extrusion artifacts. And yeah, you can print faster, and yeah, it looks okay, but it's not the optimal thing. So that's why I wanted to work in a constant jerk planner, which I naively thought it would be a lot easier, but it's not. So now what I did was I just set the maximum jerk of this trajectory generator to 8,000 millimeters per second squared, cubed, sorry. This is not classic jerk. This is not what Marlin calls jerk. This is the derivative of acceleration. And with that we can see that the acceleration profile becomes smooth. The acceleration plot now has trapezoidal phases in it, and jerk is bound. So it's not a very high peak as it used to be and then nothing. It is now different phases of constant, well-defined jerk. And if you're thinking this looks like S-curves, yes it does, but there is a big difference. The way S-curves work, like Poly 5 and Poly 6, is they start with the trapezoidal profile, and then they just fit a polynomial to the acceleration and to the deceleration phase. And this polynomial has the same initial and final speed and the same average acceleration, and it travels the same distance as the linear ramp does, but has a smooth acceleration. The issue with it is that if we have a short acceleration ramp, for example, if you're traveling making a short segment, actually let me, for the example, make it long but lower nominal velocity. This makes it more clear. Yeah, and if we feed an S-curve here, then the S-curve is going to be a lot more aggressive than if we have it to feed it to this. And what this results in is in very aggressive acceleration curves, and also unbound jerk curves. So like we did not get rid of the problem. The extruder will still suffer, and resonances will still come back for these cases. Whereas on a jerk control planner, we don't get this issue. If I now make the nominal speed shorter, you can see that acceleration and jerk still have the exact same peaks as they used to have. It's just gonna take a bit longer to ramp up and down. And so this seems to be working fine. I can change the axis speed, and you can see how the trajectory ends at the requested speed. Same with nominal acceleration, jerk, entry speed too, and so on. Now, one detail here that I'm going to talk about more during the planner is that acceleration at start and end of blocks is fixed to 0. And the reason for that is that the planner gets a lot more complicated otherwise. So what happened during planning is one has multiple blocks in RAM at the same time, and one needs to create an optimized plan. And what an optimized plan means is that the entry and exit speed of each block is optimized so that that we don't need to slow down too much between blocks, and we end up with the highest average velocity across the whole set of blocks. So what the planner does is it maximizes the junction velocity for each block. The way it does that is by going from the first block forward and calculating how fast can I go if I just accelerate, and then do that for each block, and then do the same backwards, and then you get how fast can I move forward and how fast I can move backwards, or to say it otherwise, how fast can I slow down to reach my endpoint. And if you intersect those at all junctions, you get the optimal, that is a feasible solution that is time optimal. Now, in a trapezoidal planner, that's a lot easier than a jerk control one, because in the jerk control case, we not only need to ensure that blocks end at the same speed that the next one starts, and feasibility is not about just matching speeds at the junctions, but also accelerations need to couple perfectly between blocks. So we have two variables to optimize at the same time, and the way to do that would be to do the same process of going backwards and forwards, but this time we don't just have how fast can I reach the end of the block, but we get a set which is an envelope covering different speeds, different accelerations that we can reach, because it depends what in which way we accelerate to reach the end of the block. If we were reducing acceleration when we reach the block, then we can reach a speed, but only if that end acceleration is the right one, and so on. And the issue is that these envelopes that we get at all the junctions are not a set that can be defined with a single equation. They are hard to intersect. They are computationally very expensive. There's no way we can get all of that done and running performantly on a microcontroller. And honestly, is extremely complex to code. I didn't manage to solve the general case, even disregarding CPU, RAM, and flash limitations. But I came up with something else that I think may work. So what you can see here is 5 blocks being in the plan at the same time. I'm gonna make a couple more. We have 9 now, and you can see that each block is accelerating and slowing down to meet with the next one, and they are meeting at 10 millimeters per second. And the problem with the jerk control planner, as I said, is also accelerations need to meet. And if we set acceleration at junctions, we constrain it to be 0. That simplifies the problem because it removes a variable. But it also means that if we have a lot of small collinear segments, as happens if the printer is doing a curve, then the printer needs to spend a lot of time ramping up acceleration to then like slow down and end up at zero. That it's, even though it could, technically it never reaches a good cruise speed for the whole trajectory across blocks. So the workaround I'm working on is the following. I'm not now going to set the maximum junction speed to 100, and you can see that what we ended up with looks like a single block. So what the planner is doing is realizing that these blocks are kind of compatible because they have the same or very similar nominal speed and maximum acceleration. So what it tries to do is to treat them as a single block, back to back. Of course, this doesn't always work because this may end up exceeding the maximal junction speed of some blocks. So what the planner now does is it checks if that's the case, if it's exceeding constraints, and then it goes on and splits back these super blocks at those junctions, and then it iterates, and we end up with this, which is a good plan, which is near time optimal, and at least it covers the cases that I think we are most likely to occur during printing, and it still leads to like good printing. It should still lead to good printing times and guarantee continuous acceleration. Now, this introduces some extra problems, of course, which are that FTMotion is going to have to execute a single trajectory that goes across multiple blocks. But I don't think it's going to be a problem because while FTMotion is generating the trajectory points, it knows how much distance it traveled, so it can understand that even though it's running as calculating a single trajectory, now it crossed a block boundary, and then it can load the next block. So the rest of Marlin knows which proportions to move each axis to that block. So this should hopefully work fine still. Of course, the planner is getting new blocks all the time, so it needs to... what I'm going for is it won't take all the blocks in the planner for merging, but it would like do half and merge them and then leave the rest untouched so that the next merged thing can have enough blocks to work with. And we're gonna see how it goes, I guess. I'm not so far from getting it all this code into Marlin, so I should have more news soon.